workshop. First speaker is Yamaguchi-san from Osaka University. He will tell us about non-invertible symmetries and boundaries in 4 dimensions. Please start.
Can you hear me? Okay. Today, I would like to talk about non-invertible symmetries and boundaries in 4 dimensions. And I'm Satoshi Yamaguchi from Osaka University. And this work is based on these 2 papers that are collaboration with Koide and Nagoya. So today's main topic is figured out by this picture, how invertible or non-invertible symmetry acts on boundary. So let's start from the introduction. So the main topic of this workshop is generalized symmetry. And basically, in addition to traditional, there is some extension of the notion of symmetry. And in addition to traditional symmetry, we have some kinds of new symmetries. People found new symmetries recently, and they are very actively studied. And in this extension or generalization, the key idea is topological defect. And among those new symmetries, I would like to address so-called non-invertible symmetry. And this non-invertible symmetry is topological defects without group structure. So there are many talks about in this workshop. We had many talks about these non-invertible symmetries, and also there is a nice review by Shuhen last year. And after this review, there are also lots of progress, and they are still actively studied. And we had a very nice discussion also in this workshop. And another issue I would like to address here is quantum field theory with space-time with boundary. So there are several motivations to study boundary quantum field theory. For example, it's good to theoretical developments in quantum field theory. For example, by anomaly inflow, we can understand the anomaly in terms of 1 higher dimensions, and with one quantum field theory or SPT phase in 1 higher dimensions with boundary. And also in string theory, boundary plays quite important roles. And one of the most important objects in string theory is D-branes. And D-branes are described by boundary conditions of open strings. And also in string theory, we often consider various brane configurations in which some branes has boundaries attached to another brane. And also there are holography, a boundary QFT version of holography, so-called ADS-BCFT correspondence. And there are many topics in string theory. And another big motivation is condensed matter physics. And I think surface or boundary are very big important problems in condensed matter physics. And today, I would like to consider how this non-invertible symmetry acts on the boundary. And we already had a talk by Yunqing yesterday. And unfortunately, I couldn't heard his talk fully. But he also considers some boundary CFT and non-invertible symmetry. And here I want to show some example in two-dimensional CFT. And let's take two-dimensional Ising CFT as an example. And by the famous paper by Cardi, the simple conformal boundary conditions are completely classified. So there are only three simple conformal boundary conditions, universality class of boundary condition. So one is fixed boundary condition with spin up. And another one is fixed boundary condition with spin down. And the other one is free boundary condition. And you can easily see that this spin up boundary condition, fixed boundary condition, and the spin down fixed boundary condition are related by spin flip symmetry. So they are related by usual symmetry. And interestingly, this fixed boundary condition and free boundary condition are related by kind of generalized symmetry, so-called Kramers-Wanier duality. This is a most famous example of non-invertible symmetry. And this is related to free boundary condition by Kramers-Wanier duality. And this one is also related by Kramers-Wanier duality to free boundary condition. So by this symmetry, we can derive some physical consequences. One thing I would like to focus on today is so-called G function. And basically, this is a disk partition function or hemisphere partition function in boundary conformal field theory. Because they are related by spin flip symmetry, this is just usual symmetry, so you can go this way and also this way. So their G function must be the same. This is just usual thing. But if you use, they are related by Kramers-Wanier duality, this fixed boundary condition and the free boundary condition are related by Kramers-Wanier duality, you can derive this relation. And this square root 2 is so-called quantum dimension of this Kramers-Wanier duality effect. And the important thing is this is just depends on the symmetry, but not but independent of the detail of the dynamics. So only by symmetry you can tell this relation. And about this G functions, there is a very famous theorem, so-called G theorem. And so this G function is gives us some useful information about boundary, so-called boundary RG flow. Consider boundary RG flow. Only they form the boundary, but bulk CFT is kept fixed. Then, by such a boundary RG flow, G function of UV conformal boundary condition is always greater than or equal to IR boundary G function of IR boundary condition. So, for example, in Ising CFT, we have this relation. So this because G0 has larger degrees of freedom and G plus free boundary condition has larger degrees of freedom than fixed boundary condition. So you can never have fixed boundary RG flow from fixed boundary condition to free boundary condition. That's a consequence from this theorem. And also, actually, there is actually opposite direction is possible. There is if you deform free boundary condition by spin operator, you can go to fixed boundary condition. Depending on the sign of the coupling constant, it goes to plus or minus fixed boundary condition. So anyway, I would like to also mention about four-dimensional version of this G theorem and hemisphere partition function in four-dimensional conformal field theory with conformal boundary condition. This G function or hemisphere partition function is monotonic under this boundary RG flow. And proposed by these people, and these people gave a proof. And there are other motivations. Maybe there are many motivations to think about such thing. But for example, it's often important to find the correct normalization of vacua in a gap theory for application for physical quantities. And for example, this paper applies this non-invertible symmetry to scattering amplitude. And in that work, such a boundary non-invertible symmetry acts on the vacua or boundary, plays a quite important role. And also, existence of symmetry preserving of boundary and anomaly are related. And there are lots of work before. And this paper, they also investigated non-invertible symmetry and anomaly of non-invertible symmetry and existence of symmetry preserving the boundary. And our work should be useful to some four-dimensional version of such relation. Okay, this is short summary of my talk. We consider lattice gauge theory in 4 dimensions, 4-dimensional Z2 lattice gauge theory at the self-real point. So this is analog of 2D lattice Ising model. And we find a set of boundaries that are related by non-invertible symmetry. This is just I would like to explain later this relation, but we find a set of boundary conditions in the lattice gauge theory and how they are related by non-invertible symmetry. And also we find a relation between G functions of these boundary conditions. So this should give some constraints on the boundary RFC flow. Okay. Could you say? This one was square root 2. No, this does not depend on the topology. Topology is just disk, 4-dimensional hemisphere, partition function, yes. And this is a S3 expectation value of Kramers-Wanier-Wegner duality defect. other questions? So this is a plan. First, I would like to review for the G2 lattice gauge theory, and then study boundaries of G2 lattice gauge theory. And finally, I will summarize and give some discussions. Okay, let's start from the theory for the G2 lattice gauge theory. So for the G2 lattice gauge theory, sorry, is described by this action, and we denote this one by TK or short. And this is actually a usual Wilson's lattice gauge theory. So we consider four-dimensional cubic hypercubic lattice and put spin degrees of freedom at each link. So it's like a group putting a group element to each link in lattice QCD and so on. And the action is just a bracket action. It multiplies these four spins or group elements of one bracket, and the summation over all brackets is the action. And this theory includes only one coupling constant K, one parameter K. And this K is roughly inverse coupling constant. And so if K is large, the system is weakly coupled theory. And if K is small, the system is strongly coupled theory. And yeah, please notice that this theory is different from the topological G2 gauge theory or toric code that often appears in the continuous quantum field theory. In that case, in this topological G2 gauge theory, the field strength is also always vanishes. But in this lattice gauge theory, field strength or bracket variable may trivial or may not be trivial. We consider both cases. So this theory is not topological. And also, maybe you can see that this is similar to 2D Ising model. Okay. And one of the most important symmetry of this theory is so-called center symmetry. And this is an analog of spin flip symmetry into the Ising model. And so such the symmetry is described by topological defect as this way. And the charged object is Wilson loop. And maybe for expert of such this field already know this one, and no experts cannot understand anything from this slide. So I decided to explain this center symmetry a bit more detail, because this center symmetry is quite important. This is the most typical famous example of this generalized symmetry, and one of the most useful one in four-dimensional gauge theory. So I want to explain a bit more detail about this center symmetry. So we consider this G2 lattice gauge theory, and we want to describe some transformation. And to do that, let's choose some codimension 1 surface in this lattice, like this way. Choose codimension 1 surface. And consider transformation of the link variable as this way. If link intersect to this surface even times, like for example, this link does not intersect with this one. So this one intersect this one to 0 times, so it's even. So in that case, we don't do anything for this link variable. And if it intersects odd times, for example, this link intersect this sigma once. So in this case, this link flip the sign. Let's consider such kind of transformation. So if you look, so if this surface is closed, means no boundary, then all brackets are invariant since sigma intersect each bracket even times. For example, for this bracket, 0 times intersect with this one. And for this one, for example, this is 1, 2. So it's intersect with this surface twice. So you have 2 minus signs. So this is invariant, also invariant, and so on. So it's always intersect. If this is closed, it's always each bracket always intersect with this surface twice or 4 times or even times. So since the action is just a summation over all bracket, the action is invariant by this transformation. So the naive understanding of symmetry is just by some transformation, the action is invariant. So you may call this one as symmetry, right? But actually, this description is not so convenient. In particular, it depends on the global topology of spacetime. So we have to choose a closed surface of this one. And so if spacetime is compact, actually this center symmetry is known for a long time, but it's in the context of compactified spacetime. And if it's not compactified, people did not find, how to describe this center symmetry, or at least I didn't find nice description of this center symmetry for non-compact space. So there should be a better description of this center symmetry, and that's a topological defect. So consider, so to explain this topological defect, consider codimension 1 surface and same transformation. But this time, this surface has boundary like this. Here and here are boundary, and other part just codimension 1. So but this boundary is codimension 2. And so for these brackets are invariant, and also these brackets are invariant. But for at the boundary, this bracket, for example, intersect this surface only once. So it flips a sign due to this by this transformation. So by this transformation, the action is not invariant. And at the boundary of this sigma, the action changes from the original one. So the Boltzmann way becomes this one instead of this one. So that's what we call defect. Action is different from other part and so on. And this description by defect is more useful than original, transformation in the closed surface. For example, Wilson loop is charged object by this symmetry, and we can derive easily by this transformation the Wada-Takahashi identity for Wilson loop. Symmetry defect linked to Wilson loop. You can eliminate this symmetry defect, but with this sign flip. Okay. So due to this symmetry may spontaneously broken. There is a phase structure in this theory. And in the strong coupling limit, or k is small, then this symmetry is...
Sorry.
Yes.
Small. Do you hear me? Yeah. A small question. In the previous slide,
Yes.
We believe the symmetries are associated to defects that are topological,
Yes.
meaning that you can displace them at no cost.
Yes.
Is it easy to see from this perspective that you can move the codimension one hypersurface and that one doesn't have a cost in energy?
Yes.
Oh.
So sorry. So you asking this defect is topological because yeah, easiest way is just to move this way, or just, for example, if you choose a link value, just a change of a link variable by flip the sign here, then this one is originally minus, but by sign flip of this link, this bracket becomes normal, but this bracket becomes opposite sign. So you can just redefine the sign of this link variable. You can move this one to this one. Right. Energies of the I'm not quite sure energy of two configurations are same. At least any partition function, or for example, partition function must be the same. It's a change of variable of the summation variable. Yes. Yes. Right.
So the one-form symmetry is generated by codimension 2 surface.
Right.
But here you are talking about codimension 1 surface.
Yes.
Sigma is sigma. So
this sigma is codimension 1, and its boundary is codimension 2.
but the topological operator that generates this one-form symmetry is a codimension 2 in space-time.
Right.
So
and sigma is not topological operator, but this boundary of sigma is topological operator.
Boundary. But what is a sigma?
Sigma is just auxiliary surface. Okay, thank you for many questions. And let's go to the phase structure. If it's strongly coupled in the confinement phase, or this center symmetry is preserved. And if it's in the confinement phase, the center symmetry is spontaneously broken. And so there are many terminology here saying the same thing. And this confinement phase is trivially gapped phase. And the confinement phase is topologically ordered phase. It's the same as 3+1 dimensional toric code. And this confinement phase, we only have a single vacuum for any topology of the space. But in the confinement phase, we have vacuum degeneracy, depending on the topology of the space. So this M is space, not space-time, three-dimensional space. And typically we choose T3 because we are only considering cubic lattice. But still, we have non-trivial vacuum structure in T3.
Was this result obtained by numerical simulation or some other analysis?
Okay, good questions. For weakly coupled theory, we can evaluate it by hand. And for strongly coupled phase, we can also do the same as strong coupling expansion, and we obtain area law. And of course, their symmetries are different, so there must be a phase transition. The non-trivial thing is the only one phase transition or not. And that only one phase transition occurs is checked by, I think, numerical. Yes.
Yeah. Is there a notion of weak or strong coupling in the Euclidean lattice? I can understand weak or strong coupling in the Hamiltonian picture by taking the continuous time limit. But on the Euclidean lattice directly, can you discuss weak or strong coupling?
I naively says gauge coupling constant is small. I just say weak.
Okay, in your terminology, K large, is it weak coupling or strong coupling?
K large is weak coupling.
Okay.
K is roughly 1 over G square. Maybe you can find this one from reaction. This one. K is just 1 over G square. So in the gauge coupling sense, K is large is weakly coupled. Okay. And I have to say that yeah, as Honda-san's questions, this one is a nice has many nice simulation result, and these people check that at this point the phase transition is first order phase transition, and this is one different point from the 2D Ising model. In 2D Ising model, it's second order phase transition, but here we have first order phase transition. And so we want to look at this phase transition point, and actually because this is first order phase transition, so there is no gapless degrees of freedom, and but only there are both states exist at this phase transition point. So confinement state or the confinement state, and the confinement states include many degeneracy, and at this point, so in that sense, this point is a bit richer than, of course, this one. And compared to toric code, it's a bit richer. But anyway, it's also a gapped phase. Yes.
How do you discuss states on the Euclidean lattice?
Euclidean lattice, how do you discuss the states? So Euclidean lattice, for example, you can consider partition function of, say,そうですか。はいはい。So we consider So M is basically T3. And if you look at the partition function of this one, and this circumferences of this one is beta inverse temperature. And this partition function of this Euclidean spacetime is a canonical partition function of the quantum field theory. So by looking at that partition function, you can find the spectrum of Hamiltonian. Okay, so another quite important ingredient of this theory is so-called Kramers-Fournier-Wegener duality, and it's found by Wegener. And this center symmetry can be in this case topologically gauged. So we can topologically gauge this center symmetry, and actually you can show this relation in the same way as Kramers-Fournier duality to the Ising model. So basically, it's the relation is strong weak duality. If K is large, K tilde is small, and vice versa. And because this topological gauging does not change the thermodynamic quantity like free energy density, and phase transition implies free energy density is not analytic at that point, phase transition point. So if this theory has phase transition at K, the gauge theory also has phase transition. So in that sense, this theory has common phase transition point. And if we assume only one, there is only one phase transition, then it must be a self-dual point, as the same discussion as to the Ising model. So in particular, at this self-dual point, this ungaged theory and gauge theory are equivalent. And if you have such relation, you can construct some generalized symmetry or topological defect from such duality. So we constructed this KWW duality defect following the procedure by Arsenmon Pendry. And there are more recently we have they constructed the same defect, KWW defect in a Hamiltonian formalism. So anyway, let me shortly explain this one. Yes.
In the previous slide, K and K tilde, K and what do you mean K tilde and K?
K and K tilde are related by this one. So arc sine hyperbolic rule.
K, what is different from K tilde and K?
K and for arbitrary K, you can determine K tilde by this relation.
I see. In the diagram, both are K. Or,
Yes. If, for this K, K tilde is here.
I see. Thank you.
This is just sketchy, so I don't know. This is not exact at all. But this just shows that strong and weak are related. So I want to avoid the four-dimensional figure, so I just express everything in terms of two-dimensional figure. And beautiful trick by Arsemon Fendries to introduce auxiliary lattice that is dual to the original lattice. These black lattice are original lattice. So on that link, we introduce the link variables. But this blue one is just auxiliary lattice, and we do not put any degrees of freedom. And Kramers-Wanier, as the same way as two-dimensional Kramers-Wanier duality, this Kramers-Wanier duality, Wegner duality is also exchanges the lattice with its dual lattice. So in that sense, exchange this black dots and blue dots, or black lattice and blue lattice. That's a Kramers-Wanier Wegner duality. And so we can put, by that thing, we can put this and that. So that defect may be described as this way. So across this defect, blue lattice goes to black lattice, but black lattice goes to blue lattice, and so on. They are exchanged. And this is the ansatz for this duality defect. And we want to find the weight, Boltzmann weight for this building block of this duality defect by imposing the topological relation, so that the weight of building block is determined so that this defect becomes topological. And yes, the conclusion is there is an answer. And so this is just sketchy, so and the detail is quite involved, but please remember that we put auxiliary lattice. That's important thing. And by Kramers-Wanier Wegner duality, this auxiliary lattice and active lattice are exchanged. And anyway, we can compute, once you find the weight of the building block, we can compute this, for example, S3 partition function. And we found that it's 1 over square root 2.
What do you mean compute it on the lattice? I didn't understand. How can you compute S3 partition function on the lattice?
Sorry, not partition function, but expectation value. So compare.
Yeah, it's the G function. You mean the G function?
No, this is not G function, but
okay.
This is just Kramers-Wanier Wegner duality defect of the shape S3.
Yeah, that's what's called the G function of a defect, no?
No, that's space-time does not have boundary, but just
for a topological defect, the G function is the S3 partition function, right?
Oh, okay. So maybe in that sense, this is a G function of this defect.
Okay, thank you.
Yes. So in that sense, this is smaller than 1 means there is some degrees of freedom on this surface. Okay, then let me go to the boundary. And in order to find a boundary example of the boundary, we put this ansatz. Because this duality exchanges blue lattice and black lattice, inactive and active lattice. So we consider two roughly two kinds of boundary conditions that should be related, that seems to be related by this Kramers-Wanier duality. So one boundary condition is just at the boundary, this is inactive lattice, blue lattice. So there's no link variables on this one. And so we put any boundary conditions on this one. And this one is already bulk. These black lattices are already bulk, so we do not put any boundary conditions. So this one corresponds to a free boundary condition or Neumann boundary condition. We denoted by just n. And on the other hand, this black, if at the boundary, boundary is this black or active lattice, we should impose some boundary condition at the boundary. So one way to do it is just really purely Dirichlet boundary conditions. We just impose all links at the boundary plus one, trivial, completely trivial gauge field transformation at the boundary. And they are completely not dynamical at the boundary. This is this one is just Dirichlet boundary condition, and that we denoted by D. However, we can also consider some other boundary conditions. Not all links are plus one, but all brackets are trivial. They just impose a boundary condition not for gauge field, but field strength. So at the boundary, the configuration is flat, but the boundary is not completely boundary gauge field is not completely non-dynamical, but still we sum up overall configuration at the boundary. That's a detailed boundary condition. And we want to find a precise description of more precise description of these boundaries, and also how they are related by KW duality. By the way, for purely Dirichlet boundary condition, we can also consider not only completely trivial boundary condition for A, but also you can impose another boundary condition for flat gauge field. But still it's completely non-dynamical. So Dirichlet boundary condition is labeled by the some gauge field, flat gauge field configuration on the boundary. But anyway, this is a sketch how we obtain that boundary condition. So in this AMF Asenmon-Fendry's approach, it's not easy to find the fusion rule first. So our way to do this one is to first consider the junction of this one. This is one boundary condition, and this is another condition. And this is Kramers-Wanier duality defect. And we consider the junction. And we can determine the junction weight and the boundary Boltzmann weight and so on by imposing topologicality of this junction. So this must be equal to this one. The boundary junction is just topological. So we can determine the all the Boltzmann weight and so on by this relation. By using that, we can find this kind of identity. This is hemisphere at around the boundary, and here is one boundary, and this here red one is another boundary, and this blue boundary are identical one. And you can eliminate it by eliminating this semi-hemisphere by the cost of some number. And so this is a kind of Ward-Takahashi identity. And by this, from this Ward-Takahashi identity, you can obtain the ratio of hemisphere partition function. And this is a result. And if you remember, first of all, in 4D, smaller g is has larger degrees of freedom. So g tilde is d tilde is the smallest. So d tilde boundary condition has the largest degrees of freedom, and gd is the largest. So gd d boundary condition has the smallest degrees of freedom. That's agree with the intuition. This is purely Dirichlet, and this includes some degrees of freedom. So it's completely intuitive. And Neumann boundary condition is in the middle. And by this relation, you can also guess the fusion rule. This square root 2 is the S3 expectation value of Kramers-Wagner duality. So here is a fusion rule for boundary and this topological defects. For this Dirichlet boundary condition, fusion with this Kramers-Wagner duality, then you will get Neumann boundary conditions. And for n boundary condition, you will get d tilde boundary condition. And for completeness, we also write down this symmetry defect. Just change this variable. Yes, you lose the dependence of A. That's analog of Ising model. You lose the information plus or spin up or spin minus. That's similar to this is similar to that effect. Sorry, I can understand.
This is the alpha, this is not there.
Right. And because this is a gap phase, so we can relate this boundary states and maybe the vacuum. And yeah, this Dirichlet boundary condition related to this the confinement of vacuum, and this Neumann boundary condition related to this confinement vacuum. And this d tilde boundary condition is something like this one. And maybe by this relation, you may get some intuition about our boundary condition, in particular this d tilde boundary condition. Okay. So let me summarize. We consider boundary conditions for the n equal Z2 lattice gauge theory and find a relation between them. So Kramers-Wagner duality send this Dirichlet boundary condition to Neumann and Neumann to d tilde. And we also obtained the relation between G functions. And this may constrain the RG flow. Although our theory is completely gapped, so I don't expect our theory does not have any non-trivial RG flow. But as I emphasized, such relation is independent of the detail of the dynamics, so it may be applied to other system with the same symmetry. And there are a few future issues. For example, it will be interesting to consider domain because we are in the first order phase transition and many vacua, degenerate vacua. So there are domain walls between them, and their dynamics maybe are constrained by the symmetry. So I'm interested in how they are constrained. For example, tension or the theory may be constrained by those symmetries. And here is another application to n equal 4 super theory with tau equal I. We have the same symmetry in this theory, and before those topological defect stuff, we naively thought that Neumann boundary conditions and Dirichlet boundary conditions are equivalent because they are related by S duality. But more precisely speaking, if our result can apply to this system, then Neumann boundary condition has larger degrees of freedom than Dirichlet boundary conditions. And in that case, there could be a boundary RG from Neumann to Dirichlet. That may be an interesting direction. And here I want to say some kind of speculation. So for ordinary symmetry, we find some equality of G functions. And by non-invertible symmetry, we find this relation. It's not equality, but the ratio is square root. But suppose you don't know this symmetry stuff, but you only had this one. Suppose. If you find some equality of two quantities, you may suspect there is a symmetry between to exchange this one or something. And maybe you will suspect this one. But for example, if you find by some way you find this kind of relations, I think maybe we should suspect some explanation by non-invertible symmetry. If you find such relation, we find a simple ratio, but not unity between two quantities. And here is just a single example. I recently come to know that in 2D two-flavor QED, the two meson masses of two mesons are related by square root 3 in an approximation, or maybe it's exactly exact relation. But it will be very nice if you can explain this relation by non-invertible symmetry. Okay, I will stop here. Thank you very much.
Thank you for the wonderful talk. Now is a question, time for question and discussion. Any question?
So in your computation of the G function, so your topology is a 4-dimensional disk and whose boundary is 3-sphere, or is it something different?
Yes. Okay, so our topology is hemisphere.
Hemisphere.
But it's like something like a cube because we are in the lattice.
Yeah. Then so I'm asking this because so when we compare D and D tilde, it seems that basically D tilde is saying flat, but holonomy can be arbitrary.
Yes.
But if that topology of boundary is the same with S3, then
yes.
S1 non-trivial pi 1. So
right.
I don't know why they have different.
Okay, thank you for the question. Actually, this is a gauge volume. Simply this one. Yes. So in the It's purely three-dimensional F function is the same. I mean, Z2 gauge theory has larger degrees of freedom than perfectly trivial theory. And the partition function is just 1/2. It's just a gauge volume. There's no non-trivial gauge field configuration.
I also have a question. In the beginning, you mentioned G theorem. Is it supposed to be correct for any dimension?
I think there are many conjectures, and it's proved for some case. For example, two is codimension 1 in 2 dimensions and the codimension 1 in 4 dimensions. At least I know that case. But for other case, maybe there are generic conjecture, but some of them are proved, but some of them are not still just conjecture.
Other question? If not, let's thank Yamaguchi-san again.
Thank you very much for your attention.